That's good. Good to know. It's good to know. Okay, what I did, guys, for you, I had a short presentation about transformers. So since transformers are the source of all power systems that we use, so I thought to go over a couple of power system um, layout and configuration, because transformers are the source of most of the power systems that we have. And then so that's my PowerPoint presentation, and then I do have two worksheets for you, and I would like to generate some discussion how to size. Basically, I took if you look in the left side here in the upper right corner, I took 3 transformers, grouped them on a switchgear and a feeder, and we sized everything that they need. We sized a circuit breaker one time, a fuse, um, or a fuse or a circuit breaker, a feeder on the primary side, on the secondary side, as well as a panel. And also these are for the 3 transformers here, and also the feeder that feeds that 3 transformers, the panel. So I thought that's really a good discussion to generate. So I have 2 examples for you. One of them, number 7, is the most common one. The second one is kind of highly unlikely you're not going to encounter it, because the size of the transformers are too big, and we don't use them as 480, 208, 120 step-down transformers. So these 2 sheets I gave for you, I'm going to go over them, and then what I do also, guys, everything you probably have noticed that everything that I design, I always use SKM PTW to check our work, because it's really nice to verify if I can't go for lower overcomputation devices or smaller conductor and so forth. So to help me with this one, what I did, I have a sheet for you that is called the medium voltage relay. This sheet here I'll talk about it. It talks about sizing a relay for a medium voltage transformer. So we'll do it at the end. Then I do have this is a transformer, and doing coordination over current protection coordination for the transformer. So you guys have this sheet too, using a circuit breaker. Then I use the same transformer using a fuse, just in case you decided to use a fuse versus circuit breaker. And so these are smaller transformer, number 1. Number 3 here is the same thing, another transformer, except it's a bigger size transformer. So you end up with so-called adjustable circuit breakers. So you get into setting up the adjustable circuit breakers and so forth. So one with circuit breaker and the other one with fuse. So 2 examples of each one of these examples have a circuit breaker and a fuse, do coordination for them. And the last one is I'm going to leave it until the end, doing coordination using relays for the transformers. So is that exciting enough, or no? Too much? Too little? So remember, we're engineers. We tend to complicate things, do we? Not really. So let me go ahead and start with the PowerPoint presentation. And you guys are very familiar with transformers. Transformers for us are the source of the power. When you have a commercial or industrial or building, your source of power would be a transformer coming to your building. That's your source of power. That's your reference point. A lot of you guys do a lot of commercial, right? A lot of commercial, industrial, and all this heavy duty. So you don't deal with single phase transformers a whole lot typically. So a lot of you will be dealing. So this transformer, the one in that compartment here, Tamper proof transformers, that's what we see outside feeding our building. You guys have seen probably sized tons of them sitting outside to feed your building. That's usually utility transformer, though it could be also ours, but that's Tamper proof outside transformers. The ones that we deal with all the time is these ones in the bottom right here. These are your 480/208/120 transformers that step down the voltage from 480 level into a 208/120 to burn your receptacles at that voltage, or lights if you so decided. So that's the most common transformer that you guys get engaged in sizing, right? Am I right? You guys get engaged in sizing other than the receptacle transformers, what we call it, receptacle or 208/120 transformers. We don't typically size the utility type. Do you? So some on the medium voltage. Okay. Then you get into that big boy here. That's substation type transformer. That's now we get into the medium voltage and the higher volt amps. And I'll have an example about this. And this one, I don't know if you guys do a substation. When I was working at Elevate Beckett, when we do hospitals, we do what we call a substation, where you start with the high voltage section here, like 13.8, and then you put a transformer, one lineup transformer built in, and that takes it from 13.8 into 480 277, and then that will be your switch gear attached to it. You guys designed this? Commonly used in stadiums and hospitals. So the nice thing about these is, like we did Ganda, I was part of an engineer that worked in Ganda building and Mayo Clinic. What they do is they have their 13.8 distribution system in the basement, and then they take a 13.8, 13,800, that's what they call 13.8, 13,800 volt feeder from the first floor all the way to the 13th floor, and up there, that's 13.8. And there they have a substation like this that takes a 13.8 fuse disconnect on this side, and that tied to a transformer that transform it down to a level of 480 277. That's one substation we did. The other level was another substation 28 120 to feed the receptacles. That's coming. So it's really nice lineup, very expensive though, piece of equipment. So between these, I think between this one, the substation, and these little guys, and sometimes these medium voltage transformers, that's where you're going to spend a lot of time. Just a quick review. All of you are designers, so you went to school, guys, and you know what transformers are. Transformers, they step in our world, they step down the voltage to be utilized. I don't know if you guys use the transformers to step up the voltage for transmission or distribution. I don't think you do a whole lot of stepping it up. Most of what you do is you step down, we step down the voltage so you can utilize it. So bring a 13.8 to the building, we step it down at 4160, we can burn some chillers at 4160, or we take it 13.8 at one level, we step it down to 480 277 to burn our lights and chillers and so forth. So that's what we call a step down to that utilization level. A lot of us guys, deal with the transformer, and these are just very quick review here. A lot of us deal with a dry type transformers. Very few of you probably would deal with other than dry. So core and coil are open, and it's cooled by air, either conduction of air or forced air. What they do is they have big fans. Sometimes they have big fan on them, and they cool them by forced air, or they just allow the air the natural air to cool them. That's your dry type transformer. These have limitation on the watts. I think it's 1.5 meg or something like this, megavolt amp that you can get out of them. If you want to have higher megavolt amp, which is the source of your power, is a higher megavolt amp, you have to go to liquid type transformers. So if your project requires a 5 megavolt amp, or a 20 megavolt amp, that will be a 13.8 level at 4160. You have to go to so-called liquid filled. The windings, in both windings, primary and secondary, are immersed in non-toxic liquids. And what the liquid will do will cool the transformer and insulate the windings at the same time. So that's the two types that we use. Do you guys use liquid type transformers? A lot? Not a lot? A few. In the medium voltage world, you use a lot of them. So when would I use liquid type transformer? If you need more volt amps, more horsepower, more power out of the transformer. So that's what I thought. Step down the dry type transformer. Most of us will deal with the dry type transformers. Transformers are very simple. They have windings on. Isn't that cool that it still amazes me all these years being an engineer? You put a winding on this side and another winding on the other side, and they induce the voltage from no connection whatsoever between the two, electrical connection, and they induce the voltage from this to this. So that's wireless. Isn't that what wireless power is? I mean, that's literally wireless power. There's no wire between them, except the gap is very small. If you guys can generate a transformer the gap will be 50 miles, you will be the richest man or woman on earth. So meaning transfer the power, like 50 megawatt from here to Texas. Transfer it wireless. You'll be the richest man or woman on earth. That's kind of for research. Anyway, so they do it at a smaller level inside the transformer. The two windings, they induce the voltage from here to here, which means they also shift the power goes from electrical here into electromagnetic, and then electrical back again at a different voltages and currents. It always amazes me the whole idea they're not touching each other at all, the coils. Actually, they're insulated from each other, and this you still transfer this huge amount of power. Okay, so that's basically just a few things, guys, about the principle. Of course, you guys have the assumption is you are very familiar with the transformer. What I use for transformer, I use Cutler hammer information. So I thought just a couple of information from IEEE. These are credit for Cutler hammer, so I have to give him credit. These are the standard voltages, medium high and extra high and ultra high that we use for transformers in any power system. For a lot of us guys, probably we're dealing with the 4-wire. We deal a lot with the 4-wire system, so most of us are going to be here. And we talked about the advantage of 4-wire system versus 3-wire system, right? 4-wire system will give you 2 levels of voltage, so you can burn things at 480 if you want to, or 277 if you so decided. Versus if it's a 3-wire system, it gives you only 1 voltage. You know, that's a drawback if you need the second voltage. So that's that low voltage. I thought just to throw this one. In the medium voltage world, which some of you guys use, probably a lot of us are engaged in up to this level. You'll see this a lot. From 4160 all the way to 138. These are different levels. The most common ones that they use as feeders are 1247, 13.2, 13.8, and 4160. These are the levels that they use to burn. If you have a medium voltage feeder coming to your building or transformer, you're looking at one of these voltages most likely. I don't know if you guys deal with anything higher than 13.8. Typically not, though you can. That you get into the utility type, 22 and 24 or 25 or 35. So that's your medium voltage. That's where most of our world in the construction stops, at the medium voltage level. At the high voltage level, that becomes your utility side, and it becomes, these are the transmission line that are coming to Minneapolis, 115,000 volt coming to a transmission line to downtown Minneapolis to feed all these buildings. So I personally dealt with up to 138. We designed a system for a data center. We brought a feeder 138,000 volt on the primary side that take it down to 13.8. Any comments, guys, about the voltages? Because you're going to encounter these voltages for the power system as well as for the transformers. Comments, questions? When I was doing engineering, a lot of time, guys, these are from Cutler hammer again. If you guys have Cutler hammer, you can find it. The sound levels. They will come to you sometimes and say, this is a quiet area like hospitals, and they ask you, what is the sound level of this transformer? I thought, grab some of these, and it will tell you, say if your transformer, say it's a 500 kVA transformer, typical, huh? And if you are self-cooled, there's no fans, nothing. Here's the level, the noise level that's going to be at this level. The decibels, that's how much noise this transformer will do. Who cares? When you do certain design for quiet areas, that becomes a really good information to have. These are from Cutler hammer. All the manufacturers they publish this data. So if anybody asks you about the noise level of this transformer, they also, another thing I was asked in the past, noise level and losses of a transformer. So your fellow mechanical engineers will ask you, what is the losses of this transformer, heat generated losses, so we can calculate our heat. All these transformers also have losses, which is 99% of it is heat, so they can calculate their heat gain, whatever, for the building. So just be aware of that one. There's self-cooled here, there's no fans. Then there's forced air, that's when they put big fans and blow fans at them. And then this is for the liquid, of course, if you have a liquid. And if you have a dry, which is most likely you'll have a dry, the same thing, either self-cooled or fans. You can see if you have a fans, it's going to be louder. So I thought just to throw these things to be aware if you have a transformer, especially in the medium voltage, in an area that requires you to be quiet, be aware that these information are available for you. That's the worst case, fully loaded transformers, up to my knowledge. Because if the transformer is lower, there are multiple fans. The fans can turn certain fans off, especially if there's a fan. It's lowest case scenario. The worst case scenario, as far as noise. It will be lower. That's my understanding. Lower than that. That's fully loaded transformer, 100% loaded transformer. Good point. Okay, so I thought for these then what he did, again, I know you probably cannot read all this stuff, so these are directly from Cutler Hammer, so I'm going to directly go to the website and you guys can download them. I just thought if you have never been involved in and it's really nice to look at them. So let me just open them in the Cutler Hammer format here. Here you go. So here's when we have transformers, since they are the source of your power, you have multiple ways of doing business. I thought the most common one, of course, it's a delta Y. All of us guys engaged in a delta Y system. The delta Y grounded XO system, that's the most common one. That's where you bring the 480 from one side, from the other side you take a 208 120 transformer for your receptacles or equipment that run a 208. Though you can go delta delta, we use this system delta delta if you have an assembly line and you don't want the assembly line to stop for any reason, like we talked about grounding. So you can have a delta delta system. So if you have a ground fault in one phase, the system will continue to operate properly until you go schedule a maintenance time and get rid of that ground fault. So that's the first system. That's typically we use it for survivability. This one is the most common one, like I said. The rest of them, I thought, I've never encountered a Y delta system except they do them in the transmission distribution. The YY system, they use them when they transmit the power from city to city. They use a YY system, and these are the way they tie the coils inside the transformer, if anybody's wondering. So I thought just to give you guys a couple of scenarios. This one is delta center tab. Did you guys, I don't know if you ever designed a system delta center tab. They give it to you, I don't know. It's not fun. Delta center tab. You might be in a situation where you have a delta center tab like this one at the bottom. The only system, the voltage you can get out of this is 240 123 phase. So if somebody wants 240 123 phase, the only way you can get 240 123 phase is if you have a delta. They call it delta center tab. So typically a delta from here and from the other side another delta. Take one part of the windings, tie it to the ground. So that will give you a 240 phase to phase, and between two phases and the ground and the neutral, it will give you 120. That's where the high leg is, and that's why a lot of us don't design. And the third phase, the X3, between X3 and X4 here, will give you 208 that you're not supposed to use. So if you're, I don't know if do you guys involved in that? Where do you? The only time, like you said, you will probably encounter this when you walk into a building and they want to remodel a floor in the building. And you go there and you find, great, there's a lot of spaces there and I can utilize for my 20 amp branch circuit receptacles and lights. So be aware, if it's a delta, by code, by the way, if it's a delta center tab, it has to be labeled as delta center tab, and the line, the highest voltage to ground have to be labeled on the panel. So it doesn't scare it does not confuse the people. So that's the only way you can encounter it if you're doing remodeling. They never give you a delta center tab, rarely. Do you? Okay. They give you 2 transformers, 3 transformers as service. Sometimes, yeah. Absolutely. And that leg here, the X1, have to be labeled as orange. It's the high leg. You cannot connect anything between that leg and the neutral by code. So I have an example for you here too. So that's So that's the systems. I thought that systems that we can do. So moving on, so that like I want to just emphasize the system, the Y delta Y system. Where do we? Here you go. Delta Y system is the most common. This one for survivability of the system. So 1, 2, and the last one here is the 3 systems they're going to encounter. There's advantages and disadvantages for using certain system in the construction industry. You're either delta Y grounded, or your delta delta, or your delta delta center tab. These are typically the 3 scenarios that we have. Am I missing any scenarios that you guys have seen in the construction industry? So that's what I thought. Just and there's advantage and disadvantage of them. The nice thing about the delta Y um, grounded here is it will trap all the harmonics. That's why we like them. When they have harmonics, like we feed our receptacles in here, they will trap the harmonics inside the transformer and they do not reflect them back into your power system. So it traps them inside. The advantage is then they don't pollute your other power system with harmonics. That's advantage. Disadvantage is your transformers will have circulating current because of harmonics in the Y, in the delta here, and the manufacturer will design the transformers to handle this, and that will lead us into these systems. So that's what I wanted to highlight. A couple of systems. I threw a couple of these guys. I thought that, the unique transformer connection. I've never specified a system like this. Um, as you have three when you need a three-phase system, you can either have a three-phase transformer, which is almost all of us, we specify three-phase transformer. So when you need a lighting panel, 225 amp panel here, you want to feed it. You wouldn't order three single-phase transformer, you hook him up and you feed that panel. Do you typically? You can if you want to. Typically we have a box that has three windings inside it called three-phase transformers. Well, the reason why I threw this one, because like you said, if you're doing remodeling, the utility might give you this system. So here's a delta. This is just how they hook up to get you a delta. You can get here 480 or 240 systems here. It's called delta system. That's how they hook them up on the primary and the secondary side, the high voltage and the low voltage side. Delta center tab, that's what we were just talking about, where they take one of the windings here and they ground it. What you get out of this system, the only reason why, like you said, you get this system is you'll get you, like we said, this is the Y. I apologize. This is the, no, they're taking all the X's to one. Yep, this is, my apology. This is not. Can you guys put Y here? I was sleeping when I did that. This looks different. So can you put Y on it? So this is delta Y. So on the primary we get a delta, on the secondary we get a Y. And these are the most common one that you guys will be using. Here's two levels of voltages that we get, delta Y. This is my delta, one level. This one is open delta. The open delta, you probably, I've seen them in, if you do well, you guys do well houses or lift stations or things like that. You don't do lift station, well houses. They're coming there because the utility will have two transformers, cheaper for them, and they hook them up to give you a three-phase system, exactly like you're looking at on the primary side. On the secondary side, and they take one of the transformers, which is the typically fat transformer. So this typically will be, say, 75K right in here, and this typically 50K. So one of them is bigger than the other. So one of them is 50, the other one is 75. So the 75 guy can have extra 25 kW for the line to neutral load. Line to neutral, they call it line to neutral load. So in a lift station, when you have all the pumps are running at 240, so you hook them up 240 three-phase, done. Now you have a couple of lights and a couple of receptacles in that well house that you need to power, very small amount of loads, 120. You hook them up to the neutral, line to neutral. And that will get you the, in this case, phase C, which one is the wildest leg, and the way we're hooking him up right here is going to be phase B, is my wildest thing, and it has to be labeled orange like you see. So if you hook up anything 120, it has to be A, between A and neutral, or C and neutral in this case. Any comments, guys, about this system? Where do you get this system? 240, 120, three-phase. So that's called open delta. Open delta means two transformers. If you put three transformers in your center tab, that will be your center tabbed closed delta. Center tab closed delta instead of open delta. Not common, but be aware. Mistake number one, and you can see the voltages here. Here's the 208 voltage that they warn us about, that you're not supposed to utilize. I don't know, I guess between these two here. So the voltage is between 208 to that phase B. It has to be orange. You cannot use it. So if you walk into a building and you guys are doing remodeling and you see phase A, you have a circuit breaker, space, circuit breaker, space, circuit breaker. Be aware you're looking at center tab delta. either open or closed. So don't, and if you're adding a couple of receptacles, just doing a small job, and you say, oh great, now I can have a room to add a couple of receptacles, be very aware. So circuit breaker, space, circuit breaker, space, circuit breaker, and a three-phase panel. That's an indication if it's an old panel and it's not labeled that you are dealing with center tap delta. Either open or closed, doesn't matter. So which means that space, you cannot use it for line to neutral. You can use it for line to line, by the way, but not line to neutral. Any comments, guys, about these? Comments? So I thought these are unique to get them. Then I thought, yeah, I keep forgetting.
Utility only had single-phase service for the area, and the plant wanted three-phase at his building. And I'm pretty sure this is how we ended up having to do it, because there's only single-phase service available.
Okay, so you got three-phase out of a three-phase system out of a single-phase system as an open delta.
Yeah. Right.
Yeah, but you need at least 2 huts on the primary side, no?
We had 2 primary huts, so we had and we needed 3 days.
Okay, then the third, you got the third through the ground.
Yes.
Yep. So that will be your phase. So if you have phase A on the utility side and phase B is the only 2 phases coming to your area, and then what you do is you take this one to the ground on this side, right? Is that what you guys did? And then you got you an open delta system. Use the ground as a reference, or one of them. So
It's been a while, but I believe
you take one of them as a ground reference to the ground. So that's another application. Then what I said, good one. What I thought, guys, to move through, just to review the power system, because when we talk about transformer, to me, is transformer is a power system. The most common and the simplest and the cheapest power system is so-called single radial system. Is that what you guys do? Do you do single radial? So a single radial system is when you bring the power to the building, the service, with one feeder, no generator, nothing, typically, and you feed and you go with another feeder to another panel, and from the third panel, another feeder, you go with one feeder from each panel. Okay, you can see that. So I have here my 600 volt. This will be, say, let's just say this is my 4000 amp switch gear coming in here. And then I take different MCC, 1000 amp MCC here, and so forth. You can see the power is coming from the top and going all the way down to the building, or coming from one point and spreading through your building. That's the most common power system that we use, starting with a transformer. The second common, now you get, this is the cheapest design that you can do, and probably most of the building are designed this way. Sometimes they add a generator for safety, because that's the cheapest way of designing a building. They call it simple radial system, right? That's most of the building are designed this way. Now the second one here is called primary and secondary simple radial system. What they added here, if you guys see, they added primary feeders here. These are, I don't know if you're familiar with medium voltage. If you're familiar with medium voltage, 52, the number 52 is IEEE assigned the number 52 to circuit breaker. Every time you see 52, that's meaning a big fat medium voltage circuit breaker. So these will be a 13.8. So the second one is 13.8. Still radial, but you have a primary and secondary radial system. You brought to your stadium or your hospital or your sport arena 13.8 feeder to a switch gear at 13.8, and you took multiple 13.8s to go to different parts of your building. Does that make sense? Still radial though, but you brought a higher voltage level. Typically 13.8 or 41.6. I don't see a lot of 41.6. Typically, if you want to go that high, you go 13.8, get the full benefit of the voltage. So that's the second one. The third one here, these are the most common ones. And the cheapest way of designing a system, obviously the first one is the cheapest. This is the second cheapest. Now then, you get into data centers, you get into hospitals, where you have to have multiple sources of power coming to your building. Now you get into redundancy of power. That's typically getting to the utility side, so they call it loop primary, radial secondary. On the secondary side, I don't know if you guys can see right in here, these are all still radial, right? You're just taking the 480 and feeding it through the building, multiple things. On the primary side, which is all over here, I don't know if you guys can see how many feeders are coming. There's a loop. So if
if this circuit breaker is too short, look what happened. All what you have to do, this is normally closed now, this is normally closed, you open that one and you flip it to this way, and now you're getting your power from a second loop. Do you see the redundancy? Utilities are notoriously famous of doing that. Notoriously famous of doing that. Multiple switch gear, multiple ties. You hear about tie circuit breaker. You can see the circuit. If this feeder is to go, a storm knock down the transmission line or distribution line to that substation here, the primary feeder too, no problem. All what you have to do is you close this circuit breaker here. Now these two switch gears are fed from one feeder. So that's what they call it, loop primary radial secondary. Very expensive system. You would use something like this in stadiums. You would use something like this hospital, notorious and famous in data centers. Do you do double-ended unit sub? Yep. Primary radial. It's like right in here. You're feeding from, well, there are two substations. There's one coming, the substation that fed from two ends. So that's another system. Here's what you're, no, not yet, this one. This is called basic primary selective and radial secondary. The secondary, you can see still radial coming right in here, just all the way through this transformer down, one option. But on the primary side, you have a lot of selectivity. You can, if one of them trip, like I said here, you can close circuit breaker, move you. When it comes to the medium voltage or the medium voltage or utility gas type work, the survivability of the power is very, very important. So they don't want a feeder to trip to take you down. The building that you are in here, what happens if the feeder that's coming to the building right now shorts? You go home, right? You can't tell that one to a chemical factory or to a hospital or to a data center. They can't go home. So you have to have redundancy in the system. So typically they give them, especially utilities downtown Minneapolis, notoriously famous. They have networks. So these are a higher, here's probably what you looked at. This one has two sources, primary, secondary, selective. So here's all my secondary system. This is your 480 system. You can see I have a substation. This is design substation, 2-feed medium voltage. If something to happen to this feed all together, which is coming all the way here, no problem. You can isolate, open this one, isolate and open this, isolate the system, and then the two sides of the switch gear can be fit from the left side substation. So you can see it's all about redundancy. You don't want the power to go down because of they call them single point of failure. You do not want a single point of failure. So how do you avoid having a single point of failure? A single point of failure, a feeder, a fuse, a disconnect, a substation. So you loop, you have multiple loops feeding your system. So that's another source. This one is a cheaper option of that one. Instead of having, and these are, by the way, if you want to read more about them too, they are in Cutler Hammer. I love that Cutler Hammer manual. And how many of you guys have seen them? Cutler Hammer, they have that guide, their specification guide. It's unreal. So they have the description for them. This one is cheaper because they only have one substation. So you have multiple options, except they only have one transformer. You can see that feed. So normally you're feeding from one side, the power is coming in here and feeding all, right? Upon the loss of any of these systems, and there's a key, of course, because you don't need to tie them at the same time. Upon the loss of any of these substation, you can close to one transformer, cheaper, right? To feed any one of these, like N+1. This is very similar to N+1. So you need 3 transformers to feed your building. You put a 4th transformer. So if any one of these transformers here fail, one at a time, the other transformer will take over. Cheaper design system than the one before, which is this one. You can see how each one of them has a transformer here. The other one is three source spot network. Now you get into the spot, they call them spot network. This is what they use in downtown Minneapolis. They have multiple transformers any downtown city. Multiple transformers all hooked up on the primary side and on the secondary side. And they're feeding the building. So if one transformer is to fail, no problem. All the load will shift to this other transformers, and you wouldn't dump a building. You wouldn't dump the building. So you can see a lot of ties. I don't know if you guys can see that going to multiple buildings. It's called a network. Everything is interconnected. It's like imagine the grid, and you're tapping from this grid with multiple sources. So, any comments, guys? That's a top notch, basically. Typically, utilities downtown areas they use them. I've never seen a system that's a power system that we use a spot network. Two source utilities. Now goes even further. They go all the way to the utility side, and they get you two transformers, two feeders from two different transformers. That's when you get into redundancy. It's not just two cables coming from the transmission line. No, it's two transmission line or distribution line coming from two different substations. So if one substation is to get knocked down by a tornado, the other substation is far enough in another area, hopefully will take care of you. So two sources. This qualify sometimes as another source of power for your hospitals, as an emergency system. And then you get into the typical hospital. You can see now the hospitals, you add a generators on site too, emergency generator that feed the critical. You guys you do hospitals? No, you don't do hospitals. You do? So you're familiar with a system like this one, where you have your essential, non-essential system, your emergency system, and so forth, coming from on-site generator, and typically you have two sources of power coming to your building. So you can see there's redundancy at the power level, at bringing the power level, as well as redundancy right in here at the load level. So now we get into even further than that. Instead of having, I don't know if you guys can see, this is one generator feeding a lineup of switchgear and feeding everything else, right? That's allowed by code through different auto transfer switches. So you life safety and critical and so forth. This one goes even further, where you bring multiple generators, parallel them together on a switchgear, and tie them to from one side you tie them to, this case we're not tying them to the switchgear, but we're feeding different life safety and equipment and so forth. So you go further, you have multiple generators on a parallel switchgear, and you tap from this source of power. Any comments, guys? Any questions? Typically this is for hospitals, where you have another source, not just a feeder, another source of power next to you. Okay, so that's, I thought, just to go over these, because that's where the source transformers make all these configuration. I would say, dare to say 95% of you guys use a radial low voltage. You might go radial medium voltage. If you have hospitals, you have another source of power, which is generator. The high end of generator is probably switchgear. Unit substation, I thought just to show you a lineup of unit substation. We use these a lot. So here's your 13.8 coming in here. This is your, say, let's just say 2.5 megavolt MVA, and this from this side will be typically the 480 system / 120, very typical. I'm sorry, 277, believe it or not, here 277. We've done also a 208 120 substation in hospitals, 208 120 substation. And then so that's how the lineup. It's a simple radial. You have one feed coming in here. You can see that feed. So it's still simple radial. The simplest is, except you just group the transformer, you put the transformer in, and you feed with a higher voltages at 13.8. The reason why we like 13.8, guys, in bigger buildings, imagine the voltage drop when you take a feeder 480 to the 15th floor in a building. There's a huge voltage drop. So you have bigger conductors. So the higher the voltage, the better. So when you have a bigger riser, if you have a 13.8 feeder that can go all the way to the 15th or 16th floor, 36th floor, and from there, you take the voltage from 13.8 down to 480 and feed 1, 2, 3, 4 floors underneath it and so forth. That will be the best distribution system that you can design. They have loop selection for these two. What they can do, also loop selection, you can bring multiple feeders, and you can tie, so you can take these two substations, you can pick them up from two, they have selectivity on the primary side. So if this feeder is to grab on you just close this, and this is already closed, and you close that one, and now these two substations are going on feeder 1.
and vice versa. So these are the substation. Any comments, guys, before we move? So I thought if you want to talk about transformer, you have to talk about power system, because that's how we create the power system via transformers. Comments, questions, corrections? No? All right, you here now moving down. After that, we have radial system. We love the radial system, the cheapest. Now you guys deal with K-rated transformers. Most of the transformer that we use, we control over are the 28120 transformers, right? On the secondary side, most of the time. When you deal with these one, since we have a lot of harmonics right now, meaning a harmonics is any device that consume electricity, I call them sloppy eaters. That's my term for them. So the way they digest electricity, they're like my kids, they're sloppy when they eat. So they don't eat it properly like a motor. They digest it differently, which means, what does that mean, Chad? Means they create all these ugly wave. I don't know if you guys can see that. So believe it or not, that's screwy for your transformer and for your power system. So they have multiple harmonics. It adds up to a wave, and it's an ugly wave like this instead of a beautiful sinusoidal smooth wave like this one. So who cares in terms of the wave? Who cares your equipment will be overloaded and heated? Neutral and transformers. So you hear a lot K-rated transformers. K-rated transformers, remember these are delta Y transformers. So you have a delta on this side, a Y on this side here. And when it's K-rated transformers, say K13, they design them in a way, they're basically more robust, more insulation between them. They design them in a way, one way is to handle and absorb the heat generated inside, circulating inside the Y, and another way also to cancel some of the mitigation, they call them. They cancel some of these harmonics. Long story short, your equipment will live longer and function properly. So every time you have a transformer, that 28120 transformer, you want to specify some type of a K rated. The higher the K, the better the transformer would be and the more expensive. Any comments, guys, about the K-rated transformers? We hear them all the time. It's an indication of the ability of the transformer to withstand and handle and absorb the heat generated by the circulated current as a result of the harmonics into the system. That's coming from, of course, nonlinear loads, which is anything that has electronic in it. And show me anything around us that does not have electronics, from an electronic ballast here into my laptop, into the phone, into everything else, the screens. So I thought and these are again from Color Hammer. You can read more about them. Any comments, guys, about K-rated, K-factor or K-rated transformers? So when you are having a receptacle transformer, you will make sure that it's K-rated transformer, K-rated 13 or K-rated 20. Do you guys have a peripheral? Do you decide any on the K-rated? Do you decide any one of these K-rated 13 or 20? 13, the most common. Okay, so that's a thought, just to throw the K-rated. So K-rated, the ability of the transformer to absorb and handle, to really handle and withstand the heat generated by harmonics. That's what they're doing. Then with transformer also comes a very important demarcation point. They call it demarcation point, the service point. When you have a transformers, I thought these are very interesting because your transformer that's coming to your building will decide what part is your responsibility versus what part is the electrical utility's responsibility. So here's a transformer owned and operated by electrical utility. So they have something called service point. A lot of people, guys, they have, if you put your service point right in here, then from the service point to the disconnect, this is called service entrance conductors. And from the circuit to the disconnect, from the disconnect into your switch gear, that will be called feeder. Typically, for us, most of us guys, typically the fused disconnect or the circuit breaker, these two are in one, right? A lot of us, what happened is this box here is all in one, don't we? A lot of application that we do, this is all in one. So you only have service entrance coming to your building, but it doesn't have to be this way. You could have the fused disconnect outside the building and then take a feeder all the way to the switch, becomes a feeder to the switch gear. The reason why I like these ones, because it defines what a feeder is, what a service entrance conductor is, and what a service conductors are. So if you look at right here, so from the meter, if you put the service point, which the utility decide where the service point is. So right at the meter socket or MCC or termination box.
So right in here, which is typically right at the termination box, from this side, this way, this is the responsibility of you as an engineer to design it, and the owner to maintain it. From here, this way, that will be the responsibility of the electrical contractor, the utilities to maintain it. So that the demarcation point is very important. They also have something called service drop, or overhead or service lateral. These are pulled by the utilities into their meter termination box, the termination box or the meter socket. So this becomes the owner of the utility. So the utility owns up to here. So that's scenario number one. Scenario number two, utilities sometimes, guys, get you the service point right at the secondary of the transformer here. What does that mean for you? Then you have to, your responsibility when you design is start right at this point, and their responsibility right here. Typically they don't like you to mess with their transformers. So what they do, a system like this typically is they have a termination box right in between here, where they will take care of it to the termination box, right? Isn't that what you guys do if you have a bigger building? And so that's theirs. And from the termination box directly to, let me use this color here, from this point in, this is your responsibility.
So you can see how important always ask, where's the service point? When you design a system, where do you guys want a service point? Typical service point is a meter socket is a typical service point, as well as the termination box is a service point. Any comments, guys, about these? Any comments, any questions? Service conductors and feeders are sized the same. When we size service conductors and we size feeders, service entrance conductors, the code talks a lot about, I like the terminology that they use, and always being designers, guys, we have to understand them fully, the difference between service conductor, you come from the service point all the way to the disconnect, the fuse, disconnect, or circuit breaker. That's your service conductors. We install them, we size them from the service point. From the panel in here, this is not shown here, but say if I take a feeder from here and go right in here to another panel, that's, of course, that's feeder, right? And the NEC code book treat it as completely different. Article 230 talks about it. I'm sorry, 215, I believe. 215 talks about this one. 230, see how the articles even do. 230 will talk. Article 230 will talk about this section here, and of course, if you have a branch circuit, is 210. So just FYI, branch circuit in 210, feeders in 215, and 230 will be your service conductors, your service entrance conductor in service. Any comments, guys? Any questions about the layout, where the service point is? What's your responsibility? A common mistake here is how many conductors do I need from the transformer, from the point into my building? You only need 4 conductors in the 3-phase system. A lot of people pull an equipment grounding conductor with it, or there is no 4 conductors. Common mistakes among young designers is you need 3-phase and a neutral. We don't pull anything between the termination box and the service entrance equipment. So that's, I thought, just important. Here's a couple of examples, guys. You probably have installed a bunch of these. You coming, we talked about this one. If your system is, I believe it's 400 amps, if you're higher than 400 amps, you must, correct me, 400 amps or higher, you have to have a termination box. What happened, guys, for us as an engineers, when we do our load calculation, which we did two load calculation the first time I was here, when we oversize things. We do a lot of oversizing. So a building like this, or any building, you size a 4,000 amp switchgear, and when everything is up and running, you're lucky if you can get a load on it 40% of what you designed for. So utilities are smarter than us, because they have actual data that they can. We based it on best practices in NEC code book. They base their design on actual data that they pull out of every building. So they powered hundreds of hospitals, and they can tell if it's a hospital, here is what an average hospital will take, this amount of power. Because of this, then they require you to have a termination box, long story short. So what you do is you come from here, from your transformer into your termination box. Now you size your termination box, you size this one to fit your own, you buy it, you size it, to fit your own multiple feeders, and it goes into your building. So from
From this side, you might have 12 runs of number 500 here. You could probably seen that one. 500 kcm coming into this termination box, so that's why they want you to size it kcm. From their size, they might pull 8 runs or even less than that. 8 runs parallel of 500. So that's because of this, you get into the termination box. So but here's an example where the primary come in. Typically they don't allow you to put these. If you have, typically you have your CT compartment right in here, or either CT or the termination box, which is both here, and you pull. This is your side where you can pull through the first disconnect in the basement, your first disconnect here. So these are different scenarios of pulling it. That's common where you have the termination box either part of the transformer or right next to the transformer, and you pull your equipment to it. Here's another example where this is typically in downtown areas where your meter is going to be your service point. Your service conductor is coming in here, and that's where you stop right at the point. Here's another example. You can have a bus dock, busway, tons of power. If you have a tons of power, you can pull all these power into your current transformers, and your service disconnect will be right in here. So these are different scenarios, guys, of bringing the power into the building. The most common scenario is bringing a feeder into a termination box with CT cabinet, out of the termination box into your switchboard. Any comments, guys? Any questions about that? Comments, questions? So that's I'm looking at my watch here. Okay, so I thought just to show a couple of examples. This is each one of you have probably one of these. I don't know. Did I tell you guys about that little yellow book? It's really great source. I think it's a great source. It's also in it. What this helps you is they take all the most common transformers and they give you the full load amp for them. For example, here's my 30 kVA transformer, very common. At 208 level, it will give you this amount of full load amps. At the 480 level, which is the primary side of this transformer, it will give me this amount of amps. So these are no rocket science. They take the kVA divided by the voltage, primary or secondary, and 1.73. It's itemized. What's nice about these, then there are two examples that I gave you guys, is then you take these numbers and you multiply them by 1.25 or 2.5 or whatever multiplier, and you size it. Fuse disconnect, the circuit breaker, the conductors, and so forth. So Color Hammer has them, DeWalt has them, and a bunch of other guys has them. Everybody knows how to read these, so it gives you the most common ones is that we use them. Us is we use the 480. It gives you the full load amp directly from that label, so it's really nice. Now moving into the installation of transformers, so I thought this is summary of the NEC code book, guys, the overcome protection device. For transformers, when we size the feeders for the transformers, the primary feeders or the secondary feeder with transformers. When we size a feeder, guys, the question that you're going to ask yourself, is it continuous load on this transformer? If it's continuous load on any feeder, how do you size a continuous load? You take the load, you multiply by 1.25. If it's not continuous load, how do you size the feeder? You take the full load amp and you size your conductor, no multiplying by 1.25. That's the decisive factor. If you don't know, what would I know? I mean, some of it continuous, some of it not continuous. What's the worst scenario? Continuous 1.25. So that's for the conductors. Cool. Now for the overcome protection device, this is the NEC code book is very clear. I'm going to go directly into the one that's related to us a lot, guys. Primary 600 volt or less. So there are two tables in the NEC code book. The A1 table 450.3a, it deals if the primary and or the secondary were over 600 volt. B, if the primary and the secondary are less than 600 volt or less. Does that make sense? And overcome protection device, it protects transformers only and not the conductors. That's the most common, the most important things. When you size overcome protection device based on these tables, you are not protecting your conductors. You have to think of the conductors separately. We end up protecting them, but you have to
you have to also think how are you going to protect your conductors. So this table is meant to protect the transformer, primary and secondary. You have to kind of marry it with other rules that protect your conductors on the primary side and on the secondary side. So that's being aware of that. So here's the most common, a couple of examples that we can use. I'm going to focus on that one. If you have a primary and secondary protection right in here, you have maximum overcomputation device. So on the primary side, I don't know if you guys can see, you can go as high as 250, but you can go up. On the secondary side, you can go 125. If you have a fuse on the primary and a fuse on the secondary. That's how you do it. Fuse on the primary, fuse on the secondary. So you take, if you have a transformer that's 100 amp, multiplied by 250, give you 250 circuit, the 250, it's a circuit breaker. You put a 250 circuit breaker to protect the transformer on the primary side. On the secondary side, see, it's also 100 amp. And on the 100 times 125, that'll give you 125 amp circuit breaker on the secondary. That's how you size the primary and the secondary overconduction device. Be aware that this is meant to protect the transformer, not the conductor. So you're going to think, how am I going to protect my conductors now after I put the circuit breakers here and the fuse, or now I want to tie to it a conductor. How am I going to protect that conductor? And I do have a couple of examples that I did for you guys. If you have no protection whatsoever on the secondary side, I don't know if you have a machine. This is typically if you have a machine, you bought a machine and you need a transformer to feed the machine direct. So you bring the voltage, primary, so the 480 here, 208, and you dump the 208 directly across that machine to burn. No overconduction device. If you were to do it this way, then no secondary whatsoever, then your overconduction device on the primary has to be 125. What I did, guys, for you, because it's all confusion, if you size your circuit breakers or fuses at 125 on the primary side and the secondary side, you are good up to 95% of the time. So ignoring all this, if you take your transformer, take the primary, multiply by 1.25, size the overconduction device, take the secondary, multiply by 1.25, size the overconduction device, you're right up to 95% of the time. There's a few situations that you might have to do coordination, and I'll show you in a second here that coordination. So that summarizes the whole mess here. Does that make sense? Summarizing the whole idea here. This one is for the transformers. Now they get into higher voltage transformers, over 600 volt. Then they have different multipliers. I want to emphasize the impedance first. This is my favorite, these two numbers. They allow you to go up to 600 times if you're using circuit breaker on the high voltage side. On the high voltage side. On the primary side. On the secondary side, they can, based on the fuse or circuit breaker, they allow you to go 250 or 300. If it has an asterisk next to it, means if you don't hit a fuse, like you end up with 95.3 amps. What do you do if it's 95.3 amps? You go up if it has that little asterisk next to it. So anyway, so these are summarizing the whole overconduction device for transformers. I'm going to get you guys a couple of examples. Here's an example. Let's go directly into this example and go over sizing the conductors, right? And then we'll go through the sheets. And I picked 2 sheets for you. Each sheet has 3 transformers on it. They're all of them are 600 volt or less. And I do have an example if the transformer is higher than 600 volt. So let's just look at this transformer, guys. I have a 50 kVA transformer. This is very typical, a 480 primary coming, 208 secondary going out for your receptacles. So 208 on the secondary, primary is 480. Can you guys see that? Then to find the full load current of this baby, you guys you divide it by the voltage and the 1.732. So got you on the primary side. I got 60 amps on the primary side. Now, suggested size, I want to emphasize the word suggested size here. Suggested size. If you go on the primary 1.25 and on the secondary 1.25, you are right up to 95% of the time. Always. And I'll show you that one with the coordination.
So what we do is we multiply it by 1.25 because do you guys see any disconnects here? Is this, by the way, is this primary only or primary and secondary? Do you see any fuse disconnect right next to the transformer? Nothing. So this is primary protection only, right? Because the only protection that protect the transformer is on the primary. The fuse is right in here. It's the only protection. There's nothing here, no fuse. Do they have, guys, you could bring these windings out of the transformer literally and build a compartment where it has a fuse disconnect right next to it. That would be the secondary. This circuit breaker here is not the secondary of the transformer. This is not the secondary. This is downstream. Okay, so when you go there, so we size 1.25, end up with 75 amp. And we have note number 1. It says you can go up. So I go to an 80 amp circuit breaker. 80 amp circuit breaker. An 80 amp, in this case we're sizing, so I have installed next standard size 80 amp dual element time delay fuse. That's my fuse going to be an 80 amps. On the maximum size, look at the maximum size that they use. Maximum size is 2.5, give you 150. So there's a choice you have to do between 150 amp fuse and 80 amp fuse. If you use the 1.25, and I'll show you that with the coordination, you are right up to 95% of the time. If in doubt, you guys have SKM. If you're in doubt, and when you know what type of fuse you're going to use or circuit breaker, just run an SKM analysis, and I'll show you in a second. Okay, on the secondary side, the same thing. You take the full load amp, except you're going to divide now with the lower voltage, multiply it by 1.25, and that will give me the next standard up, which is give me 175. So I have 175 amp panel overcomputation device right in here. 175 right here, and I have an 80. What did we say? Maximum 150, but recommended 80 amp fuse on the primary side. Now so now that will leave you with how do you size the conductors. When you come here, now we size the fuse here, right? Now the conductors have to be sized for 175. Now remember, the circuit breaker is not going to protect the transformer. It's not going to protect the cables. They're meant, any fuse here, the way we size it is meant to protect the transformer. So long story short, when you size the overcome protection device, the conductor must match the overcome protection device of the panel. That's easy. So my conductors here are going to be rated for 175. On this side, right in here, I'm going to match the recommended though. This will be an 80 amp circuit breaker, an 80 amp fuse. So my conductors will be rated for 80 amps. My fuse will be an 80 amps on the primary side. On the secondary side, my conductors will be 175 and my circuit breaker will be 175. Match it. Any comments, guys? Any questions about that? Comments, questions? So that's I'm gonna leave this one until the end because that talks about the medium voltage, guys, and I'm gonna take you directly into the last slides about the medium voltage. I'm gonna take you directly to this sheet number 7, and let's just look at. I really would like to see your opinion about that one. Okay, so if you guys go to sheet number 1 and number 7, it says 7 on the upper left corner. So here's the situation is, you probably wouldn't encounter this exact situation, but very similar. So I have, starting from the bottom here, I have 3 receptacle panels. Can you guys see them at the bottom? That says 2-P1. These are my receptacle panels. Ahead of them is circuit breakers. That circuit breaker can be ahead of them or inside them. SKM, you have to put, when you use SKM PTW, you have to put the circuit breaker out. So these circuit breakers can be inside the panel, it's a main panel circuit breaker. Then I have a feeder coming out of the transformer. It's called O3 transformer secondary feeder. Can you guys see that? Into the transformer 01X is my transformer. Then I have the primary of the transformer. Then I have a fuse disconnect and a circuit breaker. Now you don't have to have both. You can either have a fuse disconnect or a circuit breaker. The reason why I put them this way because I need to do coordination, and in the SKM I have to put the fuse there to do the coordination. Did you guys hear me? So you don't have to have a fuse disconnect and circuit breaker. What you need either fuse disconnect or a circuit breaker. So that's to protect this this feeder, and then there's three of them. They're grouped together in a panel or in a feeder, and they're fed by another feeder that feeds the whole three transformer system. Does that make sense? So the voltage on this level here is 480. The voltage on this level here is 208. So basically three transformers, 480 on the primary, 208 on the secondary, feeding panels for receptacles, typically receptacles. They're grouped together and they're fed through an MCC. Any comments, guys, about the layout? Exactly like we did the if you guys remember the chillers and so forth, exactly like we did the chillers. Here's my assumption. The assumption is all of them are fit from at 480. Or look at the terminals, which is 99.9% of the time you're right if you do the terminals on the lugs are rated for 75. So when they size, and I'm using THHM. Okay, now here's where I think it's very important. These loads. These demand load, guys, how do you size the load for the receptacles in a commercial building? You take every receptacle that you design a building, you multiply by 180, right? And then if it's more than 10K, anything more than 10K, add them up. Anything more than 10 kVA, cut it by half. That's how we demand receptacle load in a commercial building. So if these are receptacle panels, when you do your demand, so when I say kVA demand, this 25.3, this is coming out of a load calculation that you're going to be doing. That building is going to take that, count all your receptacles, multiply them by 180 volt amp, and then anything higher than 10K, what do you do with it? Cut them by half and add them up. So that's what the demand coming from. If this panel was a lighting panel, so you have, which would be, I think it would be full to burn your lights at 120 if you have a 480, 277 in your building. So if you decided to do so, you take all your lights, multiply them by 1.25 now, because lights in a commercial building are continuous load. And that will be an add them up, and that will be your volt amp, the demand. Any question, guys, about the kVA demand? The kVA demand. It's, go ahead.
So, say it's just a receptacle panel. Well, what if you only have, I don't know, you get it all done, it's just a panel that only has 10 seconds.
You don't need to install. My rule is, you shall not install anything less than 100 amp panel. So no matter what, your cutoff for receptacle panel is 100 amp panel. So if it has one, I mean, if you decided, it goes back into how you design your power system. If you design your power system in a good way, you should have a good amount of load on your receptacle panel. But if it has like 10 loads, 100 amp panel. And you're going to size a transformer for it, right? You'd have to size a transformer for it. But we go by the kVA. So everybody knows where we got that 25.3. I did my calculation, 180 multiplied by number of receptacles, and derated them. And then I came up with this number. These are very, very important, guys, for us as an engineers and you, because that's how you're going to size your transformer. Based on this value, you're going to size your transformer. When it comes to transformer receptacle panel, the first thing you need to pick is the transformer. So I got my demand. Here's my demand. The first thing, if you can see here, I need to find the transformer size. So based on 250.3 and the volt or the info that I gave you, the next standard three-phase transformer that takes me from 25.3 is 30. The other one, this is panel 1, 2, and 3. There are 3 panels. And for the 39.5 and 65 is 45 and 75. Everybody knows where the 30 kVA, 45 and 75 came to be. These are the next standard transformer. So you start with your load. Now, if you don't know, guys, let me tell you a little secret. In bigger buildings, what we do is we use no more than 225 amp receptacle panels, and we place them in a strategic location in the building, and every floor will have 225 amp panel with a transformer that feeds it and move on. So they use standardized method of doing it if you don't mess with the load, but it goes always by the load. Okay, here's a 30 kVA transformer, 45 and 75. Now I need to find the full load secondary. DeWalt will get you guys, and I showed you that slide. Here's your full load in each one of these transformers. Any comments, guys, about finding the full load on the secondary side? The full load on the primary, now you start, the minute that you pick the transformer, you start dealing with the transformer. You forget about the load. So my load primary, the full load current to the primary, you can see all these full load current to the primary right in here. Cool. Any question about 1 and 1.1 and 1.2? These are related to the KVA and the full load primary and secondary transformer. Now number two is I need a transformer secondary overcome protection device. Now this is that one right here. I call it secondary. It's really the circuit breaker at the secondary of the transformer, which is at the same time the circuit breaker inside the panel. So here's what you're going to do. So the first, you take the full load current, you multiply by 1.25, you get you 104, and then you go down. I typically go down. You can go up, but you go down to the next standard, the maximum 100 amp panel. And I always said minimum, also 100 amp panel. So what's the difference between maximum and minimum? Maximum is if you multiply by 1.25. Minimum, if you don't multiply by 1.25. So this doesn't make a sense, because the reason why max and mini here are the same, because I don't like to go lower than 100 amp. It's not worth putting a feeder lower than 100 amp in the building. Now look at the second one. This one I have 156.3. My maximum is the next standard down, which is 150, and my minimum is 125. The 125, guys, here is actually coming from the full load amp of the transformer. You can size the panel. I don't know if you can see this one. I can size my panel minimum based on the secondary of the transformer. Can you see that? That's my minimum. If it's a demand load here, that's okay, because you already took the demand when you did the calculation here. A lot of people like to multiply by 1.25 again. So here you can decide, you can put 125 amp panel on this transformer or 150 amp panel on this transformer, depending upon have you applied the what do I prefer personally? I prefer to size it based on the minimum here, because I take care of the demand and 1.25 inside the load itself when I pick up the load. Okay, so but for this example, I believe I size it based on the max, just because we have to standardize. So here's another multiplication here. It gets you a maximum of 250 for this transformer panel. These are panels as well as circuit breakers. Or 225 amp panel. Any comments, guys, about these? I would like to hear. What do you put on a 75 kVA transformer? Do you put a 225 amp panel, or do you tie it to 250? 225? 225. And the reason why 225 works because the demand, guys, is already taking care of the 1.25. And I have this argument all the time. I say, well, it's a feeder, Chad. Yeah, I already took care of the continuous load when I size the demand. So if I took and look at that, and also jump, look at this, I jumped from 39.5 from 65 here all the way to 75. I already jumped above and beyond what my load is. So to jump again, it would be a little bit too much. Okay, so that's where you get your minimum. Again, I can't emphasize the minimum. Here's my minimum size based on directly on the load. Can you guys see that right here? So if you want to size based on minimum, you take what's the full load current of this transformer? 208. What's the next standard overcome protection device? Immediately 225. Done. That's how you come with the minimum size. And if you do it this way, you are right 99.9% of the time. Now I size the overcome protection device, which is these ones right in here at the bottom. Now I need to go find my secondary feeder, the conductors that's coming to them, right? Now these guys are sized based on the overcome protection device. So whatever these circuit breakers are, match the conductor to these circuit breakers. Match them. So for example, I have 100 amp. See how I matched the 100 amp here? I have 100. I decided to go for the highest one, and I could really easily went for the lower here. I put 150 amp circuit breaker. I matched it with the conductor. I put 250 circuit breaker on this one, and I matched it. Could I have used the 225 amp and matched it? Absolutely. Any comments, guys, how to size the secondary conductors? Your secondary conductors are going to be the feeder that's going to your receptacle panel too. The ones that's going to your receptacle panel. So that's your secondary conductors. There's something called the supply side bonding jumper. The ones who were here when we did the grounding and bonding, the wire, it's this wire here. I don't know if you guys can see it. See that green wire here that tie your panel to your transformer. The code is, this is not an equipment ground conductor. This is called supply side bonding jumper. Who cares? Who cares is they size it differently. They size the green wire here based on the feeders, not the overcurrent protection device. If you guys are doubting Thomas and you don't believe Chad, then you have to go to 250.102C and I will tell you so in an EC code book. So that's called SSBJ, is supply side bonding jumper. How did they come up with number 8 here? Very easy. You take based on 3 size size wire 3, you go to 250.66 and that will get you the size number 8, not the overcurrent protection device. Okay, so I size these supply side bonding jumper. The reason why I size it now because I want to stick them in the flex, right? You need a wire here that goes into the cable, right? You want to put them inside the flex, so it could be outside too, or the conduit. So now I have, in this case, I have 5 conductors inside that conduit, and I need to size the conduit. That's why I size them here. Any question, guys, about the supply side bonding jumper, the SSBJ? Okay, then you go to the, then the rest is history, and I hope you guys will check my calculation. There's so many many numbers here, so it's easy to flip a number. So then I size my EMT conduit. If I want to tie an EMT conduit between the two of them, typically we don't. A flexible metallic conduit, what you typically would do is you take a flexible metallic conduit and tie from here to here and from here to here with a flexible metallic conduit for flexibility and so forth, a humming of the transformer. So what I did, I sized, like we did for the motors, we size an EMT conduit and a flex. You don't use both of them, one of them. And these are the sizes of the conduits that you need. Any comments, guys, about the primary side? Now that's a secondary side of this transformer. Any comments about the secondary side of a transformer? Now on the primary side, let me jump to the primary side. My primary side, I need to size my conductors. On the primary side of a transformer, you take, I don't know if you guys can see the full load amp on the primary side, multiply by 1.25. Again, you really don't need to multiply it by 1.25 if you took the continuous load into consideration. A lot of people do. And then here's my full load, and then my primary feeder will be, here's the amps that I need to size for, and that's my primary conductor, the same thing. So basically you take the primary, multiply by 1.25, and you size conductors, assuming it's, why multiply by 1.25? Assuming it's continuous load. Could I have gone away without 1.25 on the primary? Absolutely. A lot of people like to do it though. So that's my primary side. Then I went, we have to jump actually to this because you need to size the overcurrent protection device. Then to size the overcurrent protection device, you have 2 options on the primary side. On the primary side, which is these fuses or circuit breakers here, fuses or circuit breakers on the primary side. So either you go 2.5, you multiply by this, and you end up with 90.3. That's the maximum that you can go. 2.5, that will get you 90 amps. Or the minimum, I don't know if you guys can see where the minimum is coming from. The minimum is actually coming from 1.25. Where did it go? Right in here. Can you guys see that where this number came from? So you multiply the full load by 1.25, give you 45.1, and you go to the next standard. In this case, 45 is a standard. So that's your minimum circuit breaker they can use. You can do. Same thing here. I don't know if you guys can see. Here's my minimum here. My minimum is based on this calculation right in here. So 79.8. What's my next standard? Is 80. The maximum though, maximum is based on this calculation. Let me green here. Based on this calculation right at the top. That's where your maximum and minimum. Does that make sense? Where your maximum minute? Any comments, guys, about where we come the max and minimum? If you use the minimum, let me tell you a secret. If you use the minimum, you are right up to 95% of the time. I'll show you this one with the coordination. When we do coordination, what's wrong with using the minimum? You're taking a chance when you energize your transformer will trip on an inrush. So you need to make sure you guys have SKM PTW, especially on the primary side. Go on the primary side and make sure the fuse or the circuit breaker will clear the inrush of the transformer. And that's what I'm going to show you with the SKM calculation that I did for this example. So that's your maximum and minimum. Maximum and minimum. Any comments, guys? Any questions? So you can see the difference. I mean, the difference between some of them can be substantial. Look at this one. I can go from 125 amp circuit breaker to 225 amp circuit breaker. Like there's 100 amp difference. That's money to be spent. That's less protection. The higher the circuit breaker, the less protection that you have for your power system. So that's why we tend to try to go to the minimum. Try to go to the minimum always. Any comments, guys? Any questions about that? Do we keep asking any comments, any questions, or no? Does that make sense? No corrections? Okay, so that's basically sizing the primary and the secondary for these transformers as well as the panels. Remember, there is a panel at the bottom. That's the issue with it. There's a panel. Now, the last one, I don't know how many of you guys do that, but now suppose, typically it's not, suppose these three transformers are going to be fed from a feeder, right? There's a feeder. I don't know if you can see that feeder is coming to feed these three transformers. So how am I going to size a feeder? Well, two options. Either, personally, I go exactly by the load. I don't know if you guys can see the load. I am interested in the load. What type of load do I need? So I picked up all my loads. Can you guys see my loads that I know my loads are? Could I have added my transformer sizes? Yes. What's wrong with adding all the transformers? You're overkilling, right? So I could have added 30, 45, 75, and size. That's definitely overkilling. You go by the load. So here's my load. I added all my loads. Okay, I added my loads. So I added all my loads as a kVA. Then this is kVA, remember. Then I need to find the full load amp because I'm sizing conductors. We don't size conductors based on kVA. We size it based on amps. So I got my amps. Then I multiply it by 1.25. And even the 1.25, guys, is really questionable sometimes, but for safety. Because if you took the demand into the loads, the 1.25 is already factored in. But safety, you multiply by 1.25, assuming all of them are continuous load. That's what you're doing. You're assuming all these loads are continuous load. So you get into this value here, and then you go to the next standard overcam protection device. What's the next standard overcam protection device from 195? 200 amp. That's your fuse or circuit breaker for the whole system. Now, then I need to size the feeder though. Then you match the overcam protection device. Then you match your overcam protection device. Now, the code allows you guys up to 800 amp. You guys remember the up to 800 amp? That's when you get into when you talk to contractors, say, well, I don't have to size my feeders based on 200. I can go 156. Absolutely. The code allows you to size your feeders slightly less than right here. I'm sorry, right here. Your feeders are allowed to be sized slightly less than overcam protection device up to an 800 amp. But engineered project match your overcam protection device. Any comments, guys, about that one? So my feeder is going to be a 200 amp, and my conductors are going to be 3 conductors. Why 3 conductors? I only bring in delta, 3 conductors, and 3 out. And then the last one you need to size is the equipment grounding conductor. I don't know if you guys can see that one. This one is basically, can you guys see that green wire coming in here? That green wire? That's called the equipment grounding conductor between the fuse, disconnect, or circuit breaker and the transformer. That's an equipment grounding conductor. This guy is called supply side bonding jumper. This is equipment grounding conductor. So then you size these based on 250.122, which is based on overcam protection device. So you get yourself number 8, number 6, and number 4. And then based on, now we have 4 conductors. 3 of them are number 8. Actually, 4 of them number 8 for the first one. Based on the 3 for the 3-phase and the equivalent ground conductor, I can size my conduits EMT or flex. You can see how we size the EMT and flex. Any comments how this calculation came to be, guys? Everybody knows you take the number of conductors multiplied by the cross-sectional area. All this information are coming from 250. Chapter 9, table 4 and 5. When we size your conduits, because ultimately we as the designers and engineers, we have to size conduits, right? We have to size the conduits and the wires. That's our job. Any comments, guys? Any questions? So that's probably, these are the scenarios that you're going to encounter all the time. I bet you between 100 amp and 125 and 225, these are the most common receptacle panel and receptacle transformers you're going to encounter for receptacle panels. If your load is more than 75 kVA receptacle panel, you would be better off to split it into 2. So if you have a load that's need more than 75 kVA transformer, you will be better off split. Anybody knows why would we be better off splitting it? What happened if you group all your branch circuits in one location? What happened to the voltage drop? You have a voltage drop to worry about, right? If you put your receptacle panel in one corner and you pull a branch circuit 300, 400 feet to go pick up a couple of receptacles, what happened to the voltage drop? You get into either bad voltage drop, or your conductor is going to go from number 12 into number 10 or number 8 to capture the receptacles, and that will be a full design. So that's why it's typically you take the 75 kVA transformer and a 225 amp panel and you locate them in different places in the building. Within, if you have an electrical closet, you put the closet in one location and you try to capture all the branch circuits within 100 feet. Within 100 feet, branch circuits, receptacles, that's not, you go higher than 100 feet to the furthest branch circuit, it becomes, you get into voltage drop issues. Do you guys do it differently? Any comments, any questions? Yeah. And that's why we do all this calculation, but then you have to use common sense. I mean, and that's what, yeah, I can go for a 500 kVA transformer, but you wouldn't do that. Yes, within 100 feet or less from that transformer. Otherwise, it's not a good design. Does it work? Yes. It's not a good design. Yes, absolutely. So these between 30, 45, and 75 kVA transformer, the most common transformers you're going to use for receptacle panels. Any comments, guys, about this? Now, why on earth, Chad, would you get sheet number 8 and you have a 225 kVA transformer and a 300 kVA transformer and a 500 kVA transformer? Where would you encounter something like this? You're going to encounter something like this if you have a manufacturing floor. Say you have a manufacturing floor. It's really not a good design before I start there. If you have a manufacturing floor, guys, and you have the choice in a manufacturing floor, ask for a 480 equipment. Your process equipment that you're going to buy from China or anywhere else, ask for it to be rated for 480 if you have your choice. So what if all the equipment are rated for 208, right? Now I need to step down the voltage and feed these chunk of loads concentrated in one manufacturing floor area with a panel. That's where, or a bus duct. We use a bus duct with these. That's where you encounter something like this. And it could happen. So then I took 3 examples, the same thing. I have a manufacturing floor, and I did the calculation, the KVA calculation on my loads. You have to start with the loads. I always emphasize, guys, your load is your reference point. You can't start with if you don't know, you have to make assumptions. If you don't know, you make assumption. 225 amp panel, that's good enough. 100 amp panel, but if you start with the square foot of the building and the loads. So here's, I did my demand, 215, 270, and 450. Now, if the 1.25 is included in this, which most likely is, you don't even need to multiply by 1.25 again. Okay, so the same thing as then I went to the next standard. Can you guys see that? I went to the next standard overcomputation device. right, next standard transformer. I found the full load current on the primary, in the secondary side and the primary side. Very easy. Look at this transformer. This is like a 1,388 amps. That's a lot of amps at 208. That's a lot of power. Um, on the primary, on the secondary side. Okay, then I need to size the panel. Again, you really wouldn't do that unless you have a manufacturing floor. So the same thing, guys. You take 1.25. I have the maximum and the minimum. In these cases, when it goes to these big loads, I always go personally by the minimum, and I size everything based on the minimum. And the minimum is based strictly on the full load current of the transformer. Can you guys see this transformer can pump 11388? My next standard adjustable circuit breaker, and I emphasize the word adjustable. You go higher than 1,000 amp, guys, 99.99% of the time you're dealing with an adjustable circuit breaker. So you're no longer limited to 1,200 amp and 1,600 amp. You can have in between. Okay, so is a 1,400 amp. That's so I sized everything based on the minimum, and you can see where these are coming directly based on the full load amp. Why did I do that? Because the load is so big, number one, and continuous load is already incorporated when I did my demand. When I did my demand, anything continuous load I multiply by 1.25. Okay, so we size my conductors. You can see here my minimum is 700, 900, 1,400. And my conductors, I match the overcome protection device, straightforward. The first 4 here, if anybody is wondering, the 4 is 4 runs. So you have 4 sets so we start paralleling, 4 sets. Same thing for the supply side bonding jumper. Anybody wonder why there are 2 sizes here? Supply side bonding jumper, guys, here, that one, when you parallel, you have 2 options. When you parallel, you either put 1 in each one of the sets, or you have 1 with all the sets. It's going to be outside. That's why you have 2 options here. You either, every conduit will have 1 in it, or 1 separate outside will be outside the conduits. So in this case, I threw these 2 options for you for the supply side bonding jumper. So I have either 2-aught by itself, or 2 sets of 1-aught. Why 2? Because 1 in each conduit. Any question, guys, about these? So you can see that one. Then you size the EMT and the FMC for it. The primary side, the same thing, 1.25. And then you size, you go to the next standard. On the primary side, I use the 1.25 for one reason. I use it because you need to clear the inrush on the motor, on the transformer. Go ahead. Oh, the bonding jumper. The 2, good one. That one is based on 1 set of 500. Okay, the 2 is based on 2 sets. So 2 times 500, 1,000. One of them is based on 1,000, 2 sets. The other one is based on 1 set, which is 500. Make sense? And here the same thing. One of them, that 250 is based on 4 sets. So 4 times 500, basically 2,000. And the one underneath is based on 1 set. Okay, good point. And then we get into the primary. The reason why I multiply by 1.25 here is because I want to clear the inrush of the transformer, my transformer inrush. And then I size my 350, and I matched my overcome protection device to it. My conductor matched overcome protection device, which is not a bad idea. 1.25 is not bad conductor size. And then the primary equipment around conductor is basically based on the 350, the fuse. Yep. You can. You can, under one rule. There's a tab rule for transformers. If you stay within 10 feet, then you can. So if your feeder right in here, from the transformer to the overcome protection device is 10 feet or less, then then you can. Your conductors can be, well, actually there's a one that's 10 feet between the primary, your conductor, this conductor here, and this conductor, the two, the primary and the secondary are less than 10 feet or less than 25 feet. There are two tabs. If you use the tabs 10 and 25, you can. But if you're using 1.25, I always say match the overcome protection device. I use this rule if I'm sizing my overcome protection device based on 2.5. That's way oversizing your conductor. Okay, so that's my overcome protection device 350. Same thing. You can see we matched the minimum. I use the minimum here for the primary. The minimum, which is, you can see I'm sizing the conductor based on the minimum. Then I took the feeder that feeds all of them. I took the kVA. I don't know if you guys can see all the kVA demand here, and I added 125% to them. And I size a maximum based on this number here, and a minimum based on just adding them all together. And I personally will size based on the minimum, because at this level there's so much diversity in the load that if you size based on that, look at the differences: 1400 amp versus 1200 amp, major difference. I would use with the 1200 amp because the load there's so much diversity in the load. Then you size your overcome protection device 1200 amp and your equipment and conductor, as well as the conduit that's coming to this feeder. Any comments, guys? Any questions? I know it's complicated a little bit, not too much though. So I can't emphasize. I always start with your load. You know, if you start with your load, then just match. Use the minimum, like I said here. We sized the 1388. We went and we sized the overcome protection device to the next standard, which is 1400. Any comments, guys? And I did the reference here. I hope I put all the references here for you on this side. So that's two examples. I want to go directly to the so what I did, guys, I took sheet 7. I took sheet number 7 and the 30 kVA transformer, and I did KCM analysis on it. So I took the 30 kVA, the same branch here. See that branch right here? This branch here, and I took it to KCM PTW. Am I losing it? Yeah, you're right. Taking it to SKM, PTW SKM, and I'm doing a short circuit analysis on it and coordination. Cool. So you see that 30 kVA. So let's go do the 30 kVA and show you a couple of it. And that's what, since you guys have the software, it would be really nice if you run them. So if you guys go to the one that looks like this, here's my transformer. My transformer is 30 kVA. That's the one, the first one that we sized. So here's my damage curve. I don't know if you guys can see that black stuff here. That black, that's called the damage curve of your transformer. This little dot here, this is your inrush of transformer. You need the primary of the transformer to clear the inrush, to clear your inrush right in here. So let me start from the beginning. This is the feeder that we sized. I sized my feeder much higher here. Right here is my feed. Does it look like yours? Or did they change? Yeah, it should be. Yep. So this is the feeder for the whole system. Maybe, do I have the riser? Yeah, here's the riser. Here's my feeder. This is the guy right here that feed the transformer and multiple other transformers here. I'm sorry, the feeder right above it, actually, above here, the feed the whole feeder. Then I'm going to go to the primary. Here's my primary overcome protection device. I want to show you how I'm setting my primary. This is a Cutler hammer. Oh no, don't do that. Does it happen to you guys when you get kicked out of the system? More often than not. So good news is we have I have them in the PDF file. So let's use the circuit breaker first. There you go. Okay, no. So here's my riser, like we said. I'm going to go directly, guys, into my primary overcome protection device. This is the primary. See how I'm sizing it based on 90? That's 90. That's based on 1.25. And can you guys see that it's clearing the inrush of the transformer? Perfect. That's all what you need. You need this to clear the inrush of the transformer. So I can't go here and use less than that. Here's how you can screw up things. If you go and let's just say you use 60, it's still actually 60 still clear the inrush of that transformer. So you need so if you go lower than that, right here, that's the point that you want your black circuit breaker here to clear. So let me go back and put it at 90. So okay, was it 90, right? Here you go, 90 kVA transformer withdrawal. So that's my coordination, and this is the setting. It's 90. And then here's my damage of my transformer, and you can see the inrush here. The secondary guy here is my secondary circuit breaker, and it's sitting at 100 amp. That's 100 amp for the panel. So you can see clearly I can protect my transformer with this circuit breaker. I allow the transformer inrush right in here. So every time, what happens if you don't allow the transformer to start? What happens if you don't clear the inrush? Every time you start your transformer, you will trip. Inrush of a transformer is like inrush of a motor. Every time you start a transformer, it's a coil. It's going to take large amount of energy to magnetize the transformer. It will trip on you. So anyway, so by running this, guys, you can prove that you can size your conductor at 125 and your overcome protection device on the primary side at 125, and you still clear. Any comments, guys? Any questions about that? So it's really nice if you guys have access to, and this is using Cutler hammer. Again, you can use any manufacturers. Typically, this is a Cutler hammer FD type circuit breaker. So I protect my transformer, and at the same time I clear my inrush of that transformer. So I'm going to go directly into clear this one, okay, and I'm going to go to the fuse. The second one, guys, should show a fuse. It looks like no change here. So what I did, so for those of us who love fuses, can't live without them. So here's a fuse. I don't know if you guys can see this fuse. If I use, here's what the fuse I use here. And again, this is, it's an LPJ fuse, recommended LPJ for transformers. The fuse size is 90. I can prove to you, can you guys see the inrush here? I can actually go for lower than this and still clear the inrush. I don't know if you guys can see that. Here's where I'm screwed up here. If your fuse is here, every time you start your transformer, it's going to trip on an inrush. So you can keep moving it. I'm sizing it up to here. I can go up to a 50 amp type of fuse, and my circuit breaker, my transformer will start and it will protect. Can you guys see? I can even go as low as 50 on this particular fuse. But typically, like I like to size it, like we said, 90, because of I already have enough juice on it to get me the 90. So where would they go? Here you go, 90, 80, and you can go from here to, there you go, my 90. So here's my 90. I'm clearing, obviously I'm clearing it. I'm protecting my transformer between the primary and the secondary. I don't know if you guys can see, between this and this, I will allow the transformer to start a run, and I will protect the transformer if there's a short circuit condition in it. Any comments, guys? Any questions? So that you might have on a one like this, you might have to actually go lower to have a better protection on your like on the damage curve of the transformer. Any comments about doing the coordination? How many of you guys use SKM? Do you, all of you? Anybody? Okay. So you can use these calculations. And so what and the last two, I did one for I can't remember what size transformer. So these are the bigger transformer. The reason why I like them, because let me see what size transformer here so you guys can pick it up. I think this is the 500 kVA. So that's sheet 8, the last transformer on sheet 8. The last transformer on worksheet 8. So I have a feeder. Here's my feeder. It's a 1200 amp feeder. My primary, here's my one line diagram. Oops, I don't have a one line diagram with it assigned to it. Here's my primary is set at 800 amp, which is the minimum. Remember how we set it at the minimum? And I adjusted it. So I'm allowing my circuit breaker to, can you guys see that right here, this leg here, moving this leg here? If I move it this way, my transformer, every time I start, it's going to trip. So you try to move the instantaneous far enough that clears the inrush. Here's my damage curve for my transformer, it's protected. And here's my secondary side, which is happy to be a 1600 amp. We plugged it, I don't know if you can see, guys, it's sitting here. It's an adjustable circuit breaker. I'm using a sensor, a frame of 1600 and a sensor of 1600, and I am cutting it or adjusting it, tweaking it to 0.9 of its capability, which will give me, I don't know if you can see here, 1440 amps. So you take basically 0.9 of 1600. That'll get you 1440, and I'm sizing everything for 1400, so I'm good. Any comments, guys, about these? When you get into a bigger system like this, I use adjustable circuit breaker just so you can, so you know that you can coordinate with adjustable circuit breakers. I believe there's one more with a fuse, the same transformer. For those of us who love the fuse and can't live without it, I have the same calculation here, except the only difference here is I use the fuse. So my overcome detection device, okay, here you go. Here you go. So that fuse here, what's the setting on that fuse? The setting, it's set at 1000 amp. It's a KAF fuse, and you can see it's clearing. I don't know if you guys can see it right here. It's clearing the inrush. So some of them you might have to go higher a little bit on the primary side to clear with the fuse. So a good example is this one. I went to 1000 instead of 800 with this particular fuse because the 800 would not, if you put it at 800, it would not clear the inrush. It will not get you an inrush. It will go right over the inrush. Can you guys see that? So you might have to go to a slightly higher fuse, depending on the type of fuse, 1000 here, to clear the inrush of this transformer. Oops. There you go. Any comments, guys? Any questions? So I thought with the calculation, you can, the reason why I'm saying this one, guys, there's a lot of typical stuff that we do, but when you have a transformer, when you deal with transformer, make sure you size. Here's the rule. The rule is you want to size the overcome detection device as low as you can and match your conductor to them. Does that make sense? That's why I say 125 on the primary and the secondary. Your overcome detection device and match the conductor to it, and 95% of the time you're right. Any comments, any questions? I keep overwhelming you with that one. I do have one example, guys, about medium voltage, so I'm going to go back to my presentation. The last slide that I had for you. Now, what happened if you have a higher than 600 volt transformer, which is very few of you probably will do. So what I have two transformer here. Each one of them, guys, is 750 kVA. 750 kVA, you can see here. 750 kVA. So okay, so is it K or M? No, this can't be M. I'm sorry. That, can you guys change this one into, that can't be an M. That will a huge. Okay, 750K. Can you guys say that to K, please? So here's 750 kVA. When you do the math on this, you get 31 amps out of each one of these transformers, right? So what I'm trying to do, guys, is I have a feeder, medium voltage feeder, and I need to feed this two substations. You have two substations, medium voltage, and you need to feed these transformers. You need to size the feeder. Okay, the first thing the code says, and by the way, before I take you there, you need to be aware of 215.2b1. If you haven't, I doubt if anybody have been there. 215.2b1. It will tell you to size a medium voltage feeder. Medium voltage feeder. If you are sizing it to feed two transformers, you take the full load amp of the two transformers, no 1.25, nothing. Add them up and size your feeder. Again, I can't emphasize, these are higher than 600 volt. So, okay, here's 31 amps. My primary overcome protection device, if you guys go to table 450.3a, it will tell you that you can multiply a fuse, 3. So give you 93 amps. 100 amp fuse is, these fuses will be, they're both the same size, will be rated for 100 amp fuses here, medium voltage fuses. Now the conductor size, you take the 31 amp to 310.50. I don't know how many of you guys been in 310.60C 77. That's where we size the medium voltage in this table. And if you go under there, it tells you you have to go to the voltage is 13.8. So it will give you a number 6 MV-90. This is a medium voltage 90-degree rated feeder. So I have a number 6 conductor that's coming and feeding both transformers. Really straightforward. When you go there, you go under the 90 and you pick the conductor that can give you 31 amps. And then now to size, this is to size the feeder that's just feed one transformer. Now to size the feeder that feeds the two transformer at the same time, you just add them up. And when you add them up, give you 62, you go to the same table and it will tell you number 6 is still good enough to feed the two transformers. When you guys go there, it'll tell you number 6 is good for, I think it's like 90 amps, so it's good enough. And that's a small size you can use at this level. You can't use less than number 6, medium voltage, at this level. So that's number 6. Now, the reason why I said I threw this one, because now this is sizing it based on the load. When it comes to the medium voltage, there are two sizes that you have to be aware of. One is based on the load, and the other one based on the short circuit withstand rating. Now, great, your number 6 will function properly under normal operating condition. Now, what happens if you have a short circuit right into this medium voltage? Would this medium voltage be able to withstand the short circuit inside it, or would it burn? How would you know, right? So in order to, if you are to know, there's you have to know, then you get into a little bit deeper, then you get up with the sitting of your overcome protection device. This is the worst scenario that could happen to you. Utilities use them all the time. If you have a short circuit of a 20,000 amp and the voltage is 13.8, and you want to allow the short circuit to sit in your switchgear for 30 cycles. 30 cycles is half a second. A cycle is 60 seconds. A half a second. This is eternity in terms of heat, baking, and shaking for your equipment. That's only allowed on medium voltage as well as switchgear design. Okay, if you allow him to sit 30, this means your conductor have to be rated to handle this heat for 30 cycles and the shaking. If you do damage, they call it the thermal damage. Based on the thermal damage and based on the sitting of your relay, your conductor must be sized up to 4 aught. So this will give you an example where when you get into the medium voltage, first size based on the full load like we did, then make sure you run SKM, or you can use it this way. Here's how it goes, guys. I have my and I'm going to go fast on that one. Here's my conductor, the short circuit rating. I don't know if you guys can see the 20 amp short circuit, and I'm allowing it to sit for 30 cycles, right? 30 cycles is 1, 2, 3. Is that it here? I think it's right in here, isn't that? That 30 cycles here, 30 cycles right in here. So here's my 20 kilo amp short circuit. These are tables that size the conductor. Anybody have seen a table like this? That's how you size conductor to withstand, if you don't have SKM, to withstand the short circuit in the medium voltage, which is a huge thing. So here's my 20,000 short circuit. That's the short circuit this cable is gonna see. And if you go down here, I don't know if you guys can see it, right all the way, just go down all the way down up to, should be here, That's where you came up with, we came up with 3-aught or 4-aught? 4-aught. That will tell you, if you want to set your, if you're smart enough to set your relay for 30 cycles, you better upgrade your size of your conductor or it will burn. Now, here's the irony is, if you allow your circuit to trip, look how interesting. If you allow your circuit breaker to trip normally within one cycle, you know, within one cycle, look what size conductor you need. Number 4. So you go from number 4 to 4-aught based on how fast your circuit breaker will trip on the medium voltage. So I threw this one, guys, to give you an idea. That's and what's the available short circuit. Because when you have a medium voltage, it's not enough under normal operating condition. It will take care of business and cook your building for you. Under abnormal operating condition, you need to be able to restart your relays and clear the fault and clean what happened, and your conductor will continue to operate. You don't want to go pull your conductor because they're charted now. Any comments, guys? Any questions about that? So that's what I thought. Here's a couple of, here's what looks like medium voltage cable. I don't know if you guys have seen them. So here's your number 6 that we, or number 4-aught that we were talking about here. And that's the ampacity based on the NDC. So this is based on different, the 4-aught and number 6. Here's number 6. Number 6 can give you 93 amps. We go from 93 amps to 330 amps. These are directly from the manufacturers of this medium voltage. Actually, this is 100. I should have used this one because ours is 90 degree. Here's my, because remember it's 90. You can either use 90 or 106. You have the option. Typically 90 is your default unless you know otherwise. And here's what you, so the example that I did is using that 90. See, MV90. That's the insulation can handle up to 90 degrees Celsius before smoke start coming out of it. Any comments, guys? Any questions? Any comments? Any questions? The last thing I want to do, show you the relay for the same system. I went to SKM and I did a relay setting. Here's I don't know you guys. Here's a medium voltage TCC. No change. Here's my riser that I'm looking at. Expand that boy. Okay, now it's gonna make a mess here for me, but okay, so here's a relay. That's my relay that's feeding this transformer. Is the transformers right in here. So if you can imagine, I know why, because this is coming at the bottom here. Okay, and this is my relay sitting right in here. When it comes to the medium voltage, guys, circuit breakers are dumb. They're muscles only. They don't do much, and you need to stick a relay. There you go. Are we in here? No, right here. All right. So you can see the relays coming here to trip the circuit breaker. So here's what that, because of lack of time here. So here's my relay, sitting of my relay here. I want to show you the the conductor damage curve. Here's my conductor that I sized, number 6. Can you guys see if I set my relay like this, my conductor here will be fried. That's a damage curve for the conductor. My conductor is going to be fried. That's why you come over here and you move it to 4. I want you to watch what's going to happen to this. You shifted your damage curve here, and your relay right here is kind of shielding it, so you're good to go. So that's why you end up with, if you have a medium voltage sizing based on the conductor side, the short circuit capability, and not just the full load current. And that's the adjustable of that relay. And what we do, and I'm going to go right here, what they do now, if the instantaneous here is on, what happened is, I'm going to go delete the instantaneous, see what's going to happen to this cable, delete the segment. Can you guys see what the relay is? So by the time the relay picks up here, your conductor right here underneath it, that blue thing, will be completely burned, because I don't have an instantaneous whatsoever. So anyway, just to give you an idea, that's coordinating with relays. You might have to upgrade your conductor in the medium voltage. Any comments? I hope it wasn't too complicated or too misleading or too. That's all I have for you guys. Next week, I believe we're going to be doing generators. Are you guys excited? Thank you, guys.